A virtual power line is not a physical conductor. It is an operational concept and an arranged set of technologies, controls and market dispatch measures that emulate or unlock additional transmission capability using the existing grid. In practice, a VPL is created by coordinated use of monitoring wide area measurements, power electronics devices FACS, HVDC converters, energy storage, controllable generators loads, dynamic line ratings and optimization dispatch software so that power can be rerouted, constrained flows relieved, or apparent transfer capacity increased without building a new physical high voltage line. Think of a VPL as a coordinated recipe that changes where and when energy is injected, absorbed, or controlled so the grid behaves like it has an extra line between two nodes. Key components: building blocks, wide area measurement system WAMS, PMUs, phasor measurement units and fast telemetry to measure voltages, angles, frequencies, and flows in real time. Energy management system, distribution management system EMS DMS and an optimization layer that runs state estimation and flow optimization. Power electronics devices, FACS, STATCOM, SVC, SSSC, UPSC, HVDC back-to-back or VSC links, and converter interfaces that can change power flows quickly. Energy storage systems, BESS and controllable local DERs, solar plus inverters used to inject/withdraw power at strategic points. Dynamic line rating DLR and adaptive protection to exploit temporary thermal headroom safely. Advanced control and market interfaces, real-time dispatch, curtailment redispatch, demand response, and settlement mechanisms. Cybersecurity and communications, encrypted low-latency links and secure gateways. How VPLs operate: high-level flow, monitoring and state estimation, PMUs and SCADA feed the EMS/DMS, compute current state, flows, angle differences and limits. Detection of congestion opportunity, optimization market signals identify a need to increase transfer between two regions, e.g., renewable surge in area A that must reach area B. Optimization and coordination, an algorithm optimal power flow constrained dispatch model. Predictive controller computes a set of coordinated actions, e.g., charge discharge a BESS, change FACS set points, temporarily raise dynamic line ratings, adjust generator outputs, curtail specific DERs. Execution, control commands are sent to field devices. FACS change series reactive compensation, converters change active power set points, BESS injects or absorbs energy, demand response signals reduce selected loads. Monitoring and rollback, the EMS continually monitors the grid, and if stability, thermal or protection margins shrink, it automatically reverses or modifies the actions. This loop runs on a timescale from subsecond for some FACS fast governor actions and PMU-based control up to minutes/hours for dispatch market redispatch decisions. Detailed procedural steps to implement a VPL project: lifecycle, assessment and feasibility, perform power flow studies, contingency analysis, and economic assessment to identify bottleneck and candidate nodes for virtual transfer. Identify available controllable assets: BESS, FACS, DERs, flexible loads. Functional design, specify control objectives: increase transfer by XMW for Y hours, provide congestion relief, or provide reserve. Choose enabling technologies and communications architecture. Prototyping and simulation, build detailed dynamic and steady-state models, EMTP, RMS and OPF, and test coordinated control strategies under contingencies. Procurement and installation, deploy PMUs, upgrade communications, install hardware FACS, BESS where required, and integrate EMS modules. Testing and commissioning, hardware in the loop tests, staged commissioning under supervision, protection coordination, cybersecurity testing. Market and regulatory integration, define how redispatch costs, BESS compensation, and curtailment are settled, obtain regulatory approvals if required. Monitoring and continuous improvement, evaluate KPIs: congestion hours reduced, MWH shifted, reliability metrics, tune controllers and update models. Control functions performed by VPLs, active power flow shaping, change injections at nodes to alter power trajectories. Voltage support and reactive flow control, using FACS STATCOM to change voltage profile and thus power transfer capability. Dynamic line rating DLR exploitation, temporarily raise permissible thermal ratings when conditions allow and control flows to safely use that extra margin. Fast congestion management redispatch, localized fast actions to relieve line overloads. Frequency and inertia support, BESS and converter control provide fast frequency response and synthetic inertia. Adaptive protection coordination, protection settings adapt when flows angles change due to VPL operations. Reserve and ancillary services, VPL resources can provide reserves, ramping, or black start support as part of coordinated operation. Benefits, avoids or defers costly transmission build-out. Using existing corridors and assets reduces permitting time and capital cost. Faster deployment, software upgrades and device installations are quicker than new towers cable projects. Improved utilization, better utilization of existing lines through active control and DLR. Increased renewable integration, moves energy from high renewable zones without immediate new lines. Multifunctional, the same assets best facts can provide multiple grid services voltage support, congestion relief, reserves. Operational flexibility, dynamic and reversible interventions tailored to system state. Disadvantages and risks, limited capacity compared with new physical line. VPLs can increase apparent capacity only up to physical and stability limits. They are not a literal replacement for a permanently required corridor. Dependency on communications and control, requires high-quality telemetry, low latency and secure comms. Failures reduce effectiveness or create risk. Cybersecurity exposure, more digital control surfaces increase attack vectors. Complexity in protection and stability, dynamic reconfiguration can cause unexpected interactions with protection systems and system dynamics if not carefully engineered. Cost of enabling hardware software, while cheaper than building an HV overhead line, the costs of fax, BES, PMUs, software and skilled staff are sizable. Regulatory and market barriers, cost allocation, compensation for services who pays gets paid, and regulatory acceptance can slow deployment. Operational limits, many actions are temporary. BES energy limited, thermal headroom temporary, so long-term sustained heavy transfer still needs physical capacity. Types taxonomy of VPL approaches, software-only market-based VPLs, use optimized dispatch, curtailment, and demand response to change net injections without new hardware. Best where flexible generation or loads exist. Hardware-assisted VPLs use fax devices, HVDC converters, or BES at key nodes to actively steer flows and provide headroom. Hybrid VPLs combine software optimization, BES, and fax for maximum control and resilience. DLR-centric VPLs rely on dynamic line ratings plus operational control to temporarily use extra thermal capacity. Their BES-fed VPLs strategically locate storage and controllable DERs at boundary nodes to emulate a virtual tie between regions. Practical examples: types of real-world pilots, BES plus coordinated dispatch. Utility places battery at a grid boundary and uses it during peak export hours to relieve a congested corridor, coordinated by EMS. Fax deployment with optimized OPF, installing a STATCOM SSSC and running real-time OPF to reroute flows around a constrained element. DLR plus topology switching, using DLR together with switching schemes and redispatch to allow temporary higher transfers during favorable weather. DER aggregation, an aggregator coordinates rooftop solar curtailment and flexible loads as a virtual tie to relieve inter-area stress. Cost of operation factors and comparative perspective, high-level view. Implementing a VPL is usually cheaper and faster than building a new high-voltage transmission line, but not free.